Hello friends, and welcome to our fifth lesson in the Lean Six Sigma. Today I decided to take a few minutes walk outside home after staying 10 days in home to take some fresh air. And as part of the safety precautions against the coronavirus, and I'd like to extend my prayer for all of you to pass that critical time and you are in better health and wellness. In the last lesson we discussed the correlation percent factor with a working example, and today we should continue to discuss in more details in statistical, and we will speak about the regression equation in both the linear and the non-linear equations with its application areas and a working example. Don't go away.
The regression equation is an extent of the correlation between the independent and dependent variables x and y, in where we can conclude a statistical equation which can be used to predict the values of y with a minimum percentage of error. So let me please repeat again this definition. The regression equation is an extent of the correlation between the independent and the dependent variables, the x and the y, in where we can conclude a statistical equation, which is known to be the regression equation, which can be used to predict the values of the y with minimum percentage of error. As examples of the regression equation applications in the material engineering, we need the regression equations to predict the material specifications, such as the tensile strength test machines, which usually extract its results in a linear diagram in where we can conclude the regression equation. To predict the value of the tensile strengths by inserting the value of the elongation value. So those gentlemen who are working in metallurgy or the materials engineering, they are very familiar with this type of machine where they use different types of materials and metal specimen. And this machine is where you fix the specimen in that area, and the jaw start to pull up the specimen till it started the cracks, and hence the machine is plotting the elongation that's happening on the specimen versus the tensile strengths. And this machine is mainly used to study these material specification. And as I highlighted, it is used to measure the tensile strengths. Another example for the regression equation is the engine performance testing machine, which can extract too many different correlations and linear diagrams, such as the prediction of the fuel consumption or the fuel efficiency by inserting the value of the speed. So you can see even we can have a prediction equation to predict the value of the fuel consumption or the fuel efficiency by inserting the value of the RPM. Now we need to speak more about the regression equation. We have mainly two types of regression, the linear and the non-linear regression equation. So in the linear regression equation, if we look to the first diagram, the dotted blue line is my linear regression line, and those are the residual points, and that's my equation where the yi is my prediction equation, the beta naught is my intercept, and the beta 1 is the coefficient of the xi. We will remark in the linear equation that we have some gaps between the residual points and the trend line. So those points are the data points which are the correlation between the x and the y, where the y is my dependent variable and the x is the independent variable. So that's why if we rely 100% on this type of linear equations, we might have some errors in prediction, in predicting the values of the y. And we will see that there will be differences between the actual value of y versus the predicted value. So that's why we usually transfer this linear equation to a quadratic equation from a second degree equation, where you can see that the shape of the trend line become a curvature one, and what you can observe is that the distances between the regression line and the residual points became very less compared with the linear equation. Now, let's have a small example. If I want to study the regression equation of a correlation between the pipe diameter and the flow rate for a specific water pump. So imagine if I have a water pump that I want to study the flow rate by inserting different type of diameter. So my dependent variable will be the flow rate, the y-axis, and my x-axis, the independent variable, will be my pipe diameter. So what you can see here is the both scatter diagram are the same scatter diagram, but the only difference is that I take the trend line, a linear equation, which is y equal to the 134.2x minus 114.75, and in the second scatter diagram we have a quadratic trend line, and the nonlinear equation is y equal 48.894x squared minus 73.6x plus 41.1. I will prefer to move now to the Excel sheet so I can show to you how we can extract those regression equation. Let's go. Okay, so here we have our table for the independent and dependent variables, the pipe diameters and the flow rate. So as I mentioned, the main point is that we want to extract a regression equation to predict the value of the flow rate by inserting any value of the pipe diameter. So let's first know how we can extract the regression equation. Simply, we highlight the both columns and we'll go to the insert, recommended charts, and you can see here that we have a proposed chart, the scatter diagram. If I make double click here, then I have my scatter diagram between the pipe diameters and the flow rate. So that will be my flow rate, and this is my diameter. The x-axis is the pipe diameter. So now if I want to draw my trend line, I just click on the trend line, on the line, then I will click with the right hand side on the mouse, I click on add trend line, and then here I have all the options of the trend line. So I will choose first the linear trend line, and downside you will see an option with a checkbox display equation on chart. I will put a check mark here, and then I can close it. Yeah, and here is my equation, my prediction equation for the linear equation. I can make it a little bit bigger so it's clear for everyone. Okay, so now if I want to get the nonlinear equation, then simply I will click again on the line diagram. I click on the right hand side of the mouse, I click on the add trend line, and I go here to the polynomial, And here I can select even the degree of the equations. As much as I increase my degree, you will see that the trend line will be almost touching the line of the scatter diagram, and the errors will be much less. So to simplify now, we will have we will say it will be okay with us to go with the second degree equation. I click on display equation on the chart, and here is my equation. I can make it a little bit bigger, and this is my prediction equation, in where if I insert any of the pipe diameter, I can predict the flow rate, the water flow rate for the water pump. Now, since that we have understood how to extract the regression equation, let's go back to our PowerPoint presentation. Okay, so now that we understood how we extracted the regression equation, now we need to go to the second step, is to understand the percentage of errors and the accuracy level of the prediction equation. So let's go. Here I plotted the both equation, the linear equation and the nonlinear equation, with the diagrams beside my tables. And what I did here is that I plotted the values of the predicted y by just inserting the values of the x. Like, for example, in the first row, you can see that if I just insert the 0.25 multiply with the 134.2 minus the 114.75, it would be minus 81.2, while the actual value was 2.4, which is an indication that I have an error of minus 83.6, which is the difference between the predicted value and the actual value. So I can get the errors of all the points by getting the differences between all the predicted and the actual values of the y. And I did the same thing for the non-linear equation. What we will have as a general observation, that the differences of the points in between the linear and the non-linear, we'll see that the errors in the non-linear is much less than the linear equation. Now, to better understand the accuracy of the prediction equation, let's have what we call the residual analysis. And the residual analysis is the difference between the actual value of the dependent variable y and the predicted value. It's called a residual. So all the points that you can see here are called the residual points, and this line is my prediction line. So for any x point I want to get the predicted value, I just go to touch from the x axis. I go upside till that I touch the line. I go horizontally, then I get my predicted value. But in fact, there is what we call the actual value. So the difference between the predicted and the actual is my error. Now, it's very important for us to measure the accuracy of the prediction and the percentage of that error. And this can be done through the calculation of the coefficient of determination of the R-square, which is considered as a statistical measure for the accuracy of the actual versus the predicted values. And to calculate that coefficient, we need to go through those equations. So let's understand first what those equations are telling me. So the first terminology, the sum of square regression, the SSR, which is the sum of the all differences between the predicted value and the y bar to the power of 2, while the average y is the average of all the actual values y. And then I go to the next equation, which is the sum of square error, the residual, which is the sum of the actual y minus the predicted y to the power of 2. I think I need to adjust my equation here. My apology for that. So let me adjust it. Yeah, here it looks better now. So let's make our presentation bigger. So this is the sum of square error, the residual, which is the sum of all the actual y minus the predicted y to the power of 2. So the actual y points, this is the one, minus the predicted y to the power of 2. Okay, and the sum of the square total, which is the SSR plus the SSE, and my coefficient determination, the R square, will be by dividing the value of the SSR over the SSE, the sum of square error. Okay, so let's go now, and we will apply those equations in our examples so we can better understand the coefficient determination, the R square. Okay, so here is my X, the diameter of the pipes, my predicted values, and here is my actual value. So in the first column, I calculated the error, which is the y minus the predicted y. And here we have it to the power of 2. And I calculated the y bar, the average value of the actual values of the dependent variable. And this is my y minus the y bar to the power of 2. And this is the predicted y minus the y bar to the power of 2. And those are the summation. And by doing that, I calculate my coefficient determination by following the equation, where I found that the SSE, the SSR is 382,202.6, which is the sum of the predicted y minus the y bar to the power of 2. And then I have my SSE, which is the 60,589.22, the sum of the differences between the y, the actual y, and the predicted y to the power of 2. And then I have my sum of the square total, which is the 382,202.6 plus the 60,589.22, which is equal to 442,791.82. And then I will just divide my SSR, which is 382,202.6, by the SST, the 442,791.82. And here we can find that the coefficient determination is 0.8631, which in other way, I can say that the accuracy percentage of the linear equation will be 86.3%, which is an indication that we have a percentage of error equivalent to 13.7%. Now, if we want to calculate the coefficient determination R squared through the Minitab, so simply the first step, I will copy paste my table on the Minitab as per the shown, and then I will go to the stat, regression, and I select the fitted line plot. It will open to me that window, and I will write, plot on the Y window the dependent variable or the response, the gallon per minute, the flow rate of the water, while the independent variable, the predictor, will be the diameters. And I select the linear because here we are speaking about the linear equation. So the Minitab will give me that very nice figure, and here I have my R squared, the coefficient of the determination 86.3%, which is the same result that we calculated manually. Okay, now if I want to repeat the same equation, the same calculation, but for the non-linear equation, and we will do the same steps we did before, but the only difference that we will choose, instead of the linear, we will go and choose the quadratic equation. And from the quadratic equation, uh, we will see our non-linear equation, which is the GPM gallon per minute equal 41.1 minus 73.6 multiplied with the diameter plus 48.89 multiplied with the diameter to the power of 2. And here, what we will observe is that the R squared, the coefficient of determination, is 98.4%, which means that the non-linear equation has a more accuracy if compared with the linear equation. So now we can conclude that the non-linear equation is a better choice for us to predict the values in as per the application that we will apply, as we have seen that the percentage of error for the non-linear equation will be much less than the linear equation. So I think now that you can repeat the same example in the manual way, in the Excel, as per the manual table, if you want to practice it for the nonlinear, to make sure that you get the same coefficient determination R squared in your practice exercise. I thank you for your good listening and watching. For the next time. Thank you.